hydrogen atom with the Bohr radius of half an angstrom is situated between two metal plates 1 millimeter apart, which are connected to opposite terminals of a 500 volt battery. So that's the potential, the voltage between the two capacitors, the two plates, within the capacitor between the two plates. What fraction of the atomic radius does the separation distance amount to roughly? Okay, so since this is a uniform field, if we know the potential, we could find the electric field, right? Because the separation distance is related to the dipole, is related to the polarization, or the dipole moment, which in turn, or the polarization, which in turn is related to the electric field. Okay. Okay, so we know that V is equal to E dot dl, right? But since this is a linear, this just becomes EL, with L being the thickness, right? So I could find now E to be, so if one of the plates is at the reference at 0, the other one would be at V at 500 volts. So E would be V over L, which would be to 500 divided by 1 times 10 to the minus 3. So this is 5 times 10 to the 5 volts per meter. Okay, so this here is the electric field. Okay, and from the electric field now, I know that the dipole moment is equal to alpha E, and since we're talking about a hydrogen atom, experimentally it's determined that from the table 1 on page 168, the newer edition, is alpha over 4 pi epsilon is 0. So alpha over 4 pi epsilon is 0. This is the experimental value, 0.667 times 10 to the minus 30. Okay, forget to multiply by 10 to the minus 30, because in the description of the table it says in units of 10 to the minus 30 meters cube. Okay, so and P is just the dipole moment of the electron cloud, right? And that would just be the charge times the distance that we are looking for, right? Equal alpha E. So that means I'm looking for the what fraction of the atomic radius does separation distance roughly amount to. So now I can solve for D to be alpha E over Q, and we just said alpha is 4 pi epsilon times 0.667 10 to the minus 30, right? Divided by Q. Okay, so this would be now, if you remember, 1 over 4 pi epsilon is 8.99 times, I believe, 10 to the minus 12. So this would be 1 over, so 4 pi epsilon is 1 over 8.99 times 10 to the 12, and this is gonna be 0.667 10 to the minus 30, and then Q, that's the charge of the electron, 1.6, because it's one atom, it has one electron, 1.6 10 to the minus 19. So D turns out to be okay, I forgot to put in the E here. The E was 5 10 to the 5. So there's a 5 times 10 to the 5 here. And this is 9, not 12. Okay, so this, plugging this in, I get 2.32 times 10 to the minus 16 meters. So you could see, as he says in the morale, the displacements are very minute, even on the atomic scale. Okay, so and we can demonstrate that by comparing it roughly to the atomic radius, right? So so divide that, so D over R. Let's get the ratio. What did we get? 2.32 10 to the minus 16, and then divide that by half an angstrom, so that's 5 times 10 to the minus 11, we get 4.64 times 10 to the minus 6. So that means it's like almost if you do this the other way around, it's you reciprocate this 1/5 10 to the 6. So R is 1/5 times 10 to the 6, the amount of separation, on the order of 100,000 more, almost 100,000 more. Okay, so that's why these are really minute. Okay, continuing on with the problem, it says estimate the voltage. So now the question wants V, right? So now they're asking for V. You would need with this apparatus to ionize the atom. Okay, when would you ionize the atom? You would ionize the atom when the electron would have moved all the way to the periphery by an amount R. So when it's right here, so that's when D, the distance of separation, is equal to the radius R, or since we labeled it small r, let's go with small r. Right? That's when would that happen, and the question is what is V, right? Okay, so we already know P is proportional to E, and we know this is in between the plates, so E is V over L, right? And this is just Q times D, and D is R, so this becomes QR, right? And so now, with L, by the way, being the same thing I used here, which is the distance between the two metal plates. Okay. Okay, so any d greater than or equal to r, that's when the electron would have escaped the electron cloud to make the hydrogen atom positively charged. That's when ionization takes place. So at the minimum, they're equal. Okay, so then V would equal LQR over alpha. Okay, so let's plug in the numbers. So we have what did we say this was? 1 millimeters apart, so that's 10 to the minus 3, and then we have Q is 1.6 times 10 to the minus 19, and then R is half an angstrom. So 5 10 to the minus 11. Alpha we said 0. Wait, did we forget? Yeah, it's good. 0.667 times 4 pi epsilon, which we already know what that is, times 10 to the minus 30. Plugging this in, we need a voltage of about 1.08 times 10 to the 8 volts. To ionize it. This is the voltage needed to ionize the hydrogen atom. That concludes this problem. This question is regarding bound charges and how to figure the electric field in a polarized material. Uniform or non-uniform polarization. In this case, polarization is not uniform. It's dependent on the distance. So we have a long rod cylinder, radius A, and we set up a permanent polarization. The mechanism by which this polarization came about is not important. We are more concerned with here with the polarization itself, since it began, and what kind of electric field it creates or it causes. Okay, so S is the usual cylindrical radial vector from the z-axis. K is constant, neglect and effects. The cylinder is long, so we don't have to worry about fringing and so on. Calculate the bound charges. So first, the outer surface charge, all right, sigma. So this came from the derivation of the potential, and it turned out that the potential is due to if a polarized object is produced by a volume charge density rho and a surface charge density sigma, and here we are, and these are called the bound charges. So we are asked to find what these bound charges are. So let's start with sigma. All right, so we know that P is equal to Ks in the S direction. So we know that equation 11 in your book 411 says that sigma B is equal to P dot N, okay, dotted with the normal vector. Okay, so this will be P, which is Ks, okay, in the S direction, dotted with vector N. Now S and N are unit vectors, and since S is the radial vector from the z-axis, so is N, so they point in the same direction, so their dot product would be 1, and therefore I would get just Ks. So that means my sigma b is just ks. Okay, let's find rho bound, right? The volume charge. So we know that this is minus the divergence of P, right? And so this would be minus the divergence of Ks I can pull the K out, it's a constant, so this becomes divergence of S. Okay, so this is the divergence in the back cover of your book in cylindrical coordinates. You could look it up. It has a three components: one in the S, one in the phi, one in the Z. However, the phi and the Z components are zero because we don't have any, right? Here we only have this is the same thing as S magnitude S hat, right? So our component in the S is just S, and so the way we evaluate this, the divergence is 1 over S d over ds, right? S times Vs, which is the S component, in of the V in the S direction, which would just be S, correct? So S times S. Okay, so this becomes K 1 over S. Now this would be S squared. The partial derivative with respect to S would just be 2S. So this would turn out to be 2K, right? So rho B equals 2K. Okay, so these are the bound charges for part A, and the question now is asking what are the units, right? Wait, is it oh, I forgot the minus sign, correct? There's a minus here, a minus here, a minus here, so this would be minus 2K. Okay, the what are the units of K? Well, think about it. This there's the surface, the volume charge density is minus 2K, so it has to have the same units as the volume charge density. So that would be coulombs, right? Charge per unit volume. So coulombs per meter cube is the units for K. Okay, so now we gotta use the bound charges with Gauss's law to find the electric field inside and outside the cylinder. Okay, for that we would need the amount of charge enclosed if I were to take a Gaussian surface. So let's start inside where S is less than A. Okay, and we're gonna consider a Gaussian surface of length L. We know if we take the bound charge and we multiply it by the volume, that will give us the charge bounded inside, right? Volume of the Gaussian cylinder. I'm taking a Gaussian cylinder for symmetry, that my Gaussian surface to be cylindrical. So rho B was minus 2K, and the volume of the Gaussian cylinder is the area of the base of a cylinder, which is pi s squared. So I'm taking my Gaussian surface to be of radius s, and times the height of the cylinder, which I choose to be L. Okay, so if this is my cylinder, and this is the z-axis, okay, I'm taking my Gaussian surface to be here, length L and radius s. L, and from here to here is s. Okay, so so this would be just that, minus 2k pi squared L. Okay, now for the surface, so this is inside. Okay, so for the surface, I would take my surface charge density, sigma, and I would multiply it by the area of the Gaussian surface, right? You could do an integral, but it comes out to be the same thing. This is hold on a second. This is the rho b is constant, so it's not depending on the distance. Here we have to do an integral, right? So I would have to integrate this over the area to get the charge, because it's dependent on s. So I would get ks, right, times or sorry, this is dA, and
a little confused here because
the A,
not sure what.
no, actually never mind, because on the surface I don't really need to do an integral here, because on the surface my radius is just A, right? So this would be a constant, ks. So this would be ka. So I could just multiply by the area here, right, of the surface. So this would be sigma was ks, so ks, right,
So it'll be Ka minus 2K over 4.
times the area, which would be the area would be the circumference, 2 pi s, right, times the length of my cylinder times L. So this would be 2 pi s squared KL. And you could see it's the exact negative of Q inside, so Q total, right, which would be the sum of the two, would be 0. So there is 0 charge enclosed inside the dielectric. Okay, so now I will consider inside and outside. Okay, so now I'm inside, so S is less than A. So I'm gonna apply Gauss's law. So EdA on a closed integral is equal to Q enclosed over epsilon, and this would be E inside my Gaussian surface. This is 2 pi SL. Q enclosed, that's the Q inside, depending where you are, that's minus 2k pi s squared L over epsilon. Simplify this and we will get E to be, now remember this is radially symmetric, so this will be in the S direction, right? so I could put an S hat here, and we're gonna get 2 pi, the L goes away, independent of the length of the cylinder. S goes away, so I'm gonna get K minus KS over epsilon, minus KS over epsilon in the S hat direction. So this would be my electric field inside, right? And outside, for S greater than A, clearly if I take a Gaussian surface outside, Q enclosed will equal 0, right? We just proved that here. Q total is 0. So that means the electric field will equal 0. Okay, moving on to part C. Finally, find the electric displacement D inside and outside the cylinder. Okay, so this is equation 21. The displacement, the electric displacement, is equal to epsilon E plus the polarization. And we have the electric field both inside and outside, right? So if we go inside, so this is S less than A, we have D equal epsilon. E turned out to be minus KS over epsilon in the S hat direction, plus the polarization, the polarization is given, it's KS in the S hat, and you could see when we add these two, we get inside D equals 0. Okay. Now, outside, where S is greater than A, we know that E turned out to be 0 here. This is 0 vector. And there's no P, right? Because he said, imagine we could somehow set a permanent polarization. S is the usual from the z-axis. Okay, fair enough. So so that tells me that there's no polarization there, right? So P there would have to equal 0. And if I plug it in the same equation here, epsilon E plus P, I get outside D equals 0. Okay, and then it says prove that verify Griffith's equation 423, Gauss's law, D field works out. Okay, so equation 423 is says that the closed integral of D dot dA is equal to Q F enclosed, free charge enclosed, right? Okay, so what's the free charge enclosed? Right? It's 0, right? So this is 0. We just proved that. So that means the integral of D dot dA equals 0. So that's why D is equal to 0 everywhere. and that verifies that equation 423 works. That